So in this video, we're going to establish a formula for taking the derivative of composite functions, and that formula is going to be called the chain rule. We're going to use the definition of the derivative to come up with it. The claim is that if we want to take the derivative, d dx, of composed functions, so we read this f composed with g, and another way to say f composed with g is to say f of g of x. If we want to find the derivative of f of g of x, we just take the derivative of f at g of x times the derivative of g with respect to x. So we want to show why this will give us the derivative of a composed function. So the tool that we've been using this semester is the difference quotient. We take the limit as h goes to 0 of the difference quotient because that is the definition of a derivative. So to find d dx of composed functions, the difference quotient says first, everywhere you see an x, replace the x with x plus h, and then subtract from that the original function. So I have set up the difference quotient here. It's all over h. We're taking our limit as h goes to 0. And then once we have the difference quotient set up, we can try to manipulate things to get them into a useful form. So on the second line, we have g of x plus h minus g of x over g of x plus h minus g of x. So this is what's going on right here. This is actually equal to 1 as long as this denominator isn't equal to 0. So all I'm doing on this line is taking the original expression right here and bringing it down. So there it is, it's just replicated. So I'm taking that original expression and multiplying it by something that's equivalent to a 1. And multiplication by 1 will change how it looks, but I'll have an expression that's equivalent to what I started with. And the reason for choosing g of x plus h minus g of x is if I do g of x plus h minus g of x over h, I actually have the difference quotient being applied to the function g, which will start to look like the derivative of g. And then what I want to recognize is that I have a product in the denominator, right? It's denominator times denominator when you're taking a product of ratios. And these are just two functions sitting down here, and the product of functions is commutative. So I can change the order in which I'm doing the multiplication. So on the next line down, that's all that's happened. I've taken this guy and moved him underneath the other numerator and taken the h and moved him underneath this numerator using the commutative property for function multiplication. And now I have the limit of a product, which we know from homework 3 that the limit of a product is the same as the product of the limit. So the next line down, that's all we do is break the limit of the product up into the product of the individual limits. And when we look at this one right here, the limit as h goes to 0 of the difference quotient applied to the function g, this is just the derivative of g by definition. And then this guy, he looks ugly and nasty, but what we want to recognize is that this is just one of the alternate formulations of the derivative that we saw in video 2. So in video 2, we said, hey, if you want to find the derivative of a function at b, you can take f of a minus, I'm going to give myself a little bit of room. You can take f of a minus f of b, a delta y, divided by a delta x, so an a minus b, and you take the limit on that as a goes to b. And as a goes to b, this term goes to 0, which is what gives us the derivative. And what I want to recognize is that this right here is just this formulation for the derivative. In this case, g of x is b. So I have a b and I have f of b sitting here where b is equal to g of x. And here I have g of a where a is just equal to x plus h. Excuse me. So I have g of a, f of a in the numerator position. So I have an f of a minus f of b over a minus b. And what I want to recognize is that as h goes to 0, my a here my a is actually equal to g of x plus h. A is equal to g of x plus h. So a is the whole g of x plus h. So I get the f of a minus g of a, f of a minus f of b over g of, over a minus b form from here. Got to go careful. So what I want to think about, what happens if you take the limit as h goes to 0? Or if you take the limit as h goes to 0, g of x plus h becomes g of x plus 0. G of x plus h just becomes g of x. So if b is equal to g of x and a is approaching g of x, then a is approaching b. We get the limit as a goes to b. So this is actually the derivative of f at b, but b is the function g of x. So on the next line down, you get to write that. You get to say, hey, this mess right here is just the derivative of f at g of x times this right here is just g prime of x. So that's where the chain rule comes from. This rule or technique for finding the derivative of composed functions just comes from taking the limit as h goes to 0 on the difference quotient. And there's a couple ways that this can show up. So on the previous slide, the chain rule looked like this. So if we let u equal g of x, so if we let u equal g of x, then right here we get f of u, and so f prime at g of x, because g of x is u, that becomes just, this term right here is just dy du, and then g prime is just going to equal d, if u equals g of x, then g prime of x is just du dx. And a mental way for remembering this is it's naughty, but a mental way to remember this is to think of it as the du's canceling to give us dy dx. So another formulation of the chain rule, another way that you'll see it written, depending on the textbook and what you're doing, you'll see dy dx, the derivative of f. Remember, f prime of x can be written dy dx. So another way to think about it is do a substitution, let u equal g of x, and then you have y equals f of u, because you replace the g of x with the u, and you can find the derivative by taking dy du times du dx. In the videos that follow, I'll show you using both ways of thinking about it in the examples.